Okay, everybody, when you do this problem, we have a rope extends between two poles. A 90 Newton buoy hangs from it as shown in figure 2-3A. We're going to find the tangents in the two parts of the rope. The place where all the forces meet is where the buoy is holding onto the two ropes, and you'll note that the angles are not equal. He's not in the middle of the rope, so the tensions will be different. So we want to solve for the two tensions. We will isolate this part of the system right here. The buoy is hanging on. We'll come over here. This will represent a point where this is in our free body diagram. We will draw ourselves an XY coordinate system for a start, and we will start to show the forces acting on this point where all the forces are concurrent. First force would be the weight of the buoy downward. It's the weight exerted on the buoy by the earth. You can call that on the knot if we want to go there. What the buoy is hanging on to, we'll call it a knot or point where all the forces meet, and we'll just keep it simple. That equals 90 newtons. We also see that we have a force coming up this way, the tension force up towards this side, to the right side, at 5 degrees, and that tension looks like this. That is actually tension 2 exerted on, let's call it the knot for nothing better, by rope 2 we like, or a single piece of rope. The angle, notice that this angle here is with the horizontal, which would also be this angle with the x-axis, the 5-degree angle. We have in quadrant 2 a force coming up at a 5-degree angle, looks like this. Okay. That is tension 1 exerted on the knot by rope 1. The angle is 10 degrees with the horizontal here, so it's also 10 degrees with the horizontal over here. And then we want to draw, we have two forces that are off axis, tension 1, tension 2. Let's draw the parts for these forces. The force coming out this way, this is T2x, and the vertical component would be T2y. We also have to the left the horizontal component of tension 1, which would be T1x, and then coming straight up from there we have T1y. So we resolve tension 2 and tension 1 into their perpendicular components. Next what we want to do is write conditions for equilibrium, Newton 1 equations. Well, we can see that horizontally T2x will balance T1x, so that's going to be, writing that out, that's T2x equals T1x. And we have, vertically we have T1y up plus T2y up balances the weight down, so that equation is T1y plus T2y equals the weight of the buoy. Okay, now let's expand this with the trig. T2x is the adjacent side of the triangle here, the right triangle with 5 degrees, so that'll be the cosine. So T2x will equal T2 cosine 5 degrees. T1x is the adjacent side of the triangle on the left with a 10-degree angle, so that's going to be T1x is going to equal T1 times the cosine of 10 degrees. In a similar manner, let's get the trig for T1y and T2y. T1y is the opposite side of 10 degrees. Opposite is the sine, so T1y is going to equal T1 times the sine of 10 degrees. T2y will be, it's the opposite side of this triangle over here with 5 degrees, so T2y would be T2 times the sine of 5 degrees, and that all equals W, which turns out to be 90 newtons, the weight of the buoy. Now we have two equations with two unknowns, T1 and T2. We're going to solve the simpler equation for one of the unknowns, substitute it into the larger equation, solve for that one unknown, and double back and solve for the other unknown. So solving this equation for T2, we get T2 will equal, dividing both sides by the cosine of 5 degrees, T2 will equal T1 times the cosine of 10 degrees over the cosine of 5 degrees. Next we'll take what T2 equals and substitute it in right here for T2. So what we'll have in this equation, we'll have T1 times the sine of 10 degrees plus our substitution for T2, which is going to be T1 cosine 10 degrees over cosine 5 degrees, I'm just putting in parentheses to highlight it, times what's left over from above, times the sine of 5 degrees, and that is set equal to 90 newtons. Next, what we want to do is factor out the T1 from both of these terms. So that'll be T1 factored out, and in brackets we'll have all of the trig. This will be the sine of 10 degrees plus all of this trig that we see right here, factoring out the T1. That would be the cosine of 10 degrees over the cosine of 5 degrees plus the sine, times the sine of 5 degrees, and that equals 90 newtons. Okay, now when we do the trig on a calculator, make sure you're in the degree mode, not the radian mode when you do this. We will basically find that we have T1 and all of the trig will reduce to 0.2598, and that equals 90 newtons. So to solve this for tension 1, divide both sides by 0.2598, so we'll have T1 equals 90 newtons divided by 0.2598. Plugging this into a calculator, we would see that T1 will sort itself out to be 346 newtons. Okay, now we want to find T2. We're going to double back over to here because we have the x equation for equilibrium. Solve for T2. We're going to substitute in T1. We're going to get T2 equals 346 newtons times the cosine of 10 degrees divided by the cosine of 5 degrees. And what we're going to find by doing a little bit of doing all this on the calculator, we'll find that T2 equals 342 newtons. Okay, now if we go back up to the original drawing and look at this a little bit, up top we see that T1 equals I think I labeled these wrong. Okay, we solve for no, we got it right. T1, is 346. That's this right here, 346 newtons. Thought they were reversed, they're not. And T2 is a little less, and that's 342 newtons. Now it should be a little less because the greater angle means you have to have a larger vertical component. The 10 degree will give you a larger Ty component than the 5 degree. It's only 4 newtons more, but it's not the same because the angles are not the same. So this is how you solve a problem like this, where you have two equations with two unknowns, here and here, and you solve this equation for one of the unknowns. You substitute it here, you factor out that unknown, you solve for it, and then you double back to this equation to find the remaining unknown.